Okay, so during this presentation, I would like to further advocate the use of digital twins to help us combat climate change. Before I say anything, I would like to thank the team I was part of. It was a delight to work with them, and I think it's reflected in this presentation. So we're going to propose digital twins to safeguard the planet. And so it's a big idea, and the big idea reads to develop a multi-fidelity, scalable, long-lived open source platform to build problem-specific digital twins. For those of you who forgot what digital twins are, or a definition thereof, can be found below. A digital twin is a virtual representation of an object or system that spans its life cycle, is updated from real-time data, and uses simulation, machine learning, and reasoning to help decision-making. And so on the right, we translated that to managing the Earth system, right? So we want to be able to, for instance, detect changes, to measure the response for certain climate mitigation measures we have made, de-risk through being uncertainty aware, inform policy decisions, and integrate scientific understanding and knowledge through in silico simulations. And so that all is basically representative for what we call a problem-specific digital twin. So digital twins are not all encompassing. They have focus areas, but what they do, they try to basically address all those points in that beautiful figure on the right. Okay, so why do we want to do this? Well, I think we all agree the Earth is super duper complex. As an Earth scientist, I know that. And in order to control climate or help control, we have to be able to run what-if scenarios. Because we have all limited resources, we have to make the right decisions. So techniques from causal inference, that is what-if scenarios, would be very helpful to address some of these points. Another key point I would like to make is that the rest of the world is doing this stuff already. So in Singapore, they have a digital twin for the city. Europe has several initiatives. So I think we can, as the US, not stay behind. I'm sort of biased in this because I'm working on this stuff in the context of geological carbon storage, or CCS. And that's a very complicated, very long-lived process. You inject CO2 for about 30 to 40 years. Then you have to monitor it for up to 100 years. And it's complex, and there are lots of risks that you try to mitigate. Some of them are illustrated in this figure. And so, but the concept of digital twins, it goes much further than only CCS. That's why we want to make a generic framework that allows us to do this. Okay. So what do we intersect with? Or what areas do we address? All of them, from the basic sciences to applied sciences. And so we feel we intersect with everything on the walls around us. And what I feel also, because I was the PI of a large proposal for this, digital twins have really the ability to bring a lot of different fields together in a framework that people can easily plug into. And I think that's important if you want to address complicated problems. So one way to phrase all of that is that it involves the development of a community of practice around the digital twin paradigm, which consists of protocols that enable systematic analysis of Earth system processes, including quantification and analysis of dynamic uncertainty, because things change over time. And so that's the very ambitious goal we have. Okay. What is required? It's a lot, right? So we need people from many different fields involving mathematics and physicists and chemists to inform in silico simulations that we use to train the neural networks that define a digital twin. We need statisticians to assess uncertainty and to inform policy decisions that are based on that uncertainty, and that we can make those decisions with confidence. We need scientific domain experts to develop problem-specific digital twins. They have different physics, different types of data, different remote sensing techniques, and so on. We need software engineers to write software rather than code, to make it long-lived and maintainable and reproducible. And we need social scientists to incorporate understanding of human behavior and impact in these models. Now, it lives in the computer, so we need resources, and these are massive. I did a back-of-the-envelope calculation for CCS. It takes about 3 months to train on full summit. if you want to do this on industry scale problems. So Summit is the second largest machine of the Department of Energy. So that's a lot, right? So even if you were to go to the cloud providers, they will think twice to do anything like this. And that's another very interesting aspect of it. It's long term. CCS projects inject for 30 years, monitor for 70. So you're talking about 100 years. And so we're not used to that, but that's what you need to think about if you develop these systems. So you need to software design needs to take longevity into account so that people in the next generations can actually work with your technology. And of course, it needs sustained investment and maintenance. Okay, so that brings me to the last slide. What is the broader impact? I think what's really cool is that these digital twins bring different people from different fields together in interdisciplinary teams in a very natural way, spanning fields from math, statistics, engineering, and social sciences. It will involve lots of data to train itself, but it will also produce lots of data that people can use and experiment with. So you can test different scenarios to sort of get a feeling for how much impact certain climate mitigation measures will have. It is also a prototype for global cooperation between the US and other countries. So for instance, the digital twin I'm developing for CCS is made for the world. It's not for the US, it's really an open source to help drive innovations. It will train the next generation. It needs a lot of computers already mentioned. And the expected value is that it will create the infrastructure to safeguard the planet no less. Thank you.